Hello, I'm Junmo Kim from Korea University. Today, I will introduce about some representative papers about my research and current progress. First of all, I'm doing a research about motor imagery EEG classification. EEG is an electrophysiological monitoring method to record electrical activity on the scalp that has been shown to represent the macroscopic activity of the surface layer of the brain underneath. The dataset called BCI Competition 4 was used in my research, which consists of 9 subjects with 2 sessions. Each session consists of 144 trials, 1,125 time points, and 22 EEG channels. There are 4 classes in the dataset, which are left hand, right hand, feet, and tongue. So let me introduce some CNN models which frequently used as the baseline in MI-EEG classification domain. The first paper is deep learning with CNN for EEG decoding and visualization. In this paper, 2 CNN models are proposed. Let's look at the first one. The first model is called Deep Convolution. Deep Convolution has 4 convolution max pooling blocks with a special first block designed to handle EEG input. The first convolution block was split into 2 layers in order to better handle the large number of input channels. 1 input channel per electrode compared to 3 input channels in RGB images. The first layer, each filter performs a convolution over time, and in the second layer, each filter performs a special filtering with weights for all possible pairs of electrodes with filters of the preceding temporal convolution. The exponential linear units was used as an activation function. The second one is called shallow convolution. Concretely, the first 2 layers of the shallow convolution perform a temporal convolution and a spatial filter, as in the deep convolution. In contrast to the deep convolution, the temporal convolution of the shallow convolution had a larger kernel size, allowing a larger range of transformations in the layer. After the temporal convolution and the spatial filter of the shallow convolution, a skewing nonlinearity on mean pooling layer and a logarithmic activation function follow. The next model is EGNet. The overall visualization of the EGNet architecture is shown in Figure 3. Lines denotes the convolution kernel connectivity between inputs and outputs. The network starts with a temporal convolution to learn frequency filters, then uses a depthwise convolution, which learns a temporally summary for each feature map individually, followed by a pointwise convolution, which learns how to optimally mix the feature maps together. So with this, the author of EGNet claims that the alpha feature maps of the 1D temporal convolution layer contain the EEG signal at different frequencies, which is hard to clearly understand. So in order to give more focus on the spectral and embedding, we designed two different methods that uses Wavelet Transform and multi-scale module. The first idea is to use Wavelet Transform. By using the Wavelet Transform, the raw EEG signal converts into the image with time frequency domain. Then the CNN module receives the converted images as if and learns the spatial, spectral, and temporal features. Note that the Wavelet Transform block, this blue block, can be replaced by Wavelet Corner. Wavelet Corner is the neural network that acts like the Wavelet Transform, which enables the end-to-end learning. The next idea is to use temporal corners with multi-scale. The length of the corner and the frequency are inversely related. So if we use corners with different scale like this, each corner conducts high-pass filtering with different frequencies. The architecture of this model is similar to the previous one. The EEG signal gonna be the input of the model. And after passing through the 4 multi-scale modules, consists of 5 different corners. The outputs become the input of the CNN module. Note that the CNN modules are the same with the previous method. Finally, the output feature maps or CNNs are concatenated with each other, like this. This picture shows the spectrogram of the filtered signals from 5 different corners. Note that the signal from shorter corner mainly highlights the higher frequency range, and the signal from longer one highlights the lower frequency range. So this is gonna be this picture. It's from the shortest corner, and the result picture shows that it can extract more higher range of the signal. The evaluation of our proposed methods were conducted by using the session 1 as a training set and session 2 as the test set. The second method using multi-scale module shows the best result compared to the 3 baseline models in the first proposed method. However, using the first method shows the worst performance. So in future works, we will conduct the experiment with different number of the temporal corners in the multi-scale models. And at the final part of the model, we are making various attempts to mix the output feature maps and use the attention module instead of simply concatenating the feature maps. Also, we will develop the architecture of the CNN module of the method using Wavelet Transform, as we think that the reason of the poor performance of the method is the shallowness of about CNN mode. Okay, thank you for listening.